Well, damn. I didn't make this exam hard enough. That's pretty damn good, people. I'm happy. If you've got questions, take a look at the key on our Canvas page. Um, Feel free to come talk to me. I'm pretty happy about this. Moving onward. So if I have a function of t, I can do this crazy integral and get the Laplace transform of that function, provided that Laplace transform integral converges. I'd like to be able to go the other way. If I can do this, I'm going to call the little f of t I come up with the inverse transform of capital F of S. Now, there's a distinct advantage here. We have a table. In our textbook, we have this table on our Canvas page. See right here? Laplace transforms PDF. You'll get this for the next exam. It will be attached to the exam. But this allows me a nice, easy way to do this if the function f of s is already on this sheet. I can simply work from right to left instead of left to right. So if I see something like f of s is 1 over s, okay, either open the physical textbook to the back cover, open Canvas and pull up this page, or go to your notes from Wednesday last week. Tell me, what's a function whose Laplace transform is 1 over s? It's just the function 1. I also remember that, when I had e to the something t, I got 1 over s minus a from e to the at. I have sine and cosine. And all of these same ideas, I even had powers, right? F of s was n factorial over s to the n plus 1. That came from t to the n. So when I see results in S that look like these, I know what functions they came out of, what they are the transforms of. In the same way as I did in Calc 1, when I was dealing with derivatives, integrals, u subs, I can fudge a constant. Let's ask, what is a function whose transform is 1 over s cubed? I'm serious. I'm keeping this list out for my availability. It's the inside cover of the textbook in the back. It's on our Canvas page. Pull it up, hang on to it. I'm going to need this. 1 over s cubed. Well, no, only 1 over s gives me a 1. Yeah, but multiplication doesn't work on integrals. Adding, subtracting, I can split up. Multiplying by a constant, I can kind of fake, but the product rule doesn't work for that. That's what integration by parts would be required. And I don't want to do that. I'm trying to undo the integrals. I don't want to try and do that. But I look at the formulas that are already listed on this page, and I see s to the n plus 1 in the bottom, right here. So I say to myself, oh, I should be using n equals 2, right? If I have an s cubed down here, I'd have an n cubed if I chose n to be 2, right? But if I chose n to be 2, then the Laplace transform of t squared would be 2 over s cubed. I don't have a 2. If this was a u substitution and I needed the 2, what would I do? I need the 2 and I don't have it. Which would give me 2 of them, right? So I could put a 2 in there. But that's not the way I did it when I was doing u subs or when I was doing derivatives. What did I do when I was doing u subs? If I wanted to put a 2 on the inside, I'd do something else. The only thing I'm allowed to multiply that doesn't change stuff is 1. So if I want a 2 somewhere, I have to multiply by 1. So I need a 2 over a 2. Or I need a 2 and a 1/2, right? So if I want to put the 2 in there, I should put the 1/2 out here. Like we did on the integral symbol, right? We'd take the du is 2 dt and we'd move the 2 and we'd end up with the 1/2 out front, wouldn't we? Aha, wait a second. The Laplace inverse of 1 over s cubed is the Laplace inverse of, Gesundheit, 2 over 2 times 1 over s cubed. I multiplied by 1. But we know that the Laplace transform is an integral. And integrals, you can take constants out front. So I'm going to take the 1/2 from the bottom and leave the 2 on the inside. And this would give me t squared, wouldn't it? This is the correct thing to give me the inverse t squared. But that 1/2 stays there. I've used the fact that what I've got is a linear transformation to split it up and spread it out to something I like, to something that matches a formula I already have. Cody, make sense? Yeah. But that same thing works for adding or subtracting, as well as dealing with constants that aren't right. Here, let's try the inverse transform of 1 over s squared minus 48 over s to the 5th. If it was just S on the bottom, give me 1. If it's S to any other power, I need to try and match it to that power of T idea, like we did here. So the S squared should be what power of T? T to the first. Okay. But now I have to check and see if that's actually the right formula, because it should be n factorial over s to the n plus 1. If it was t to the first, it would be 1 factorial over s to the 1 plus 1. What's 1 factorial? Perfect. So that part is right. But what I'm really doing is I'm splitting this up. And I'm just looking at the 1 minus 1 over s squared first, because it's linear behavior. And if I'm adding, I can do each one separately and add. If I'm subtracting, I can do each one separately and subtract. Oh, makes my life easier. So that's the first one. The first one should give me T minus. All right, what should go there? What's the thing that's going to give me an S to the 5th on the bottom? But if it's a T to the 4th, it should have a 4 factorial on top, right? What's 4 factorial? You own calculators. You do not have to do this crap in your head. But I have a 48, so I'm off by a factor, aren't I? Well, I can say this is really 2 times 24 over s to the 5th, right? Inverse. I forgot my minus ones. Because 48 is twice 24. Then I take this 2, put it out front. As long as I know what's on here, I can work backwards from this list. But that means separating and adjusting and rearranging as needed. I would like to know what function produces a Laplace transform of 5 over s squared plus 49. So I start looking at my list of Laplace transforms. What do you see that at least kind of matches the pattern for our Laplace transform that we want out? We want 5 over s squared plus 49. Cody? Yeah, the sign there. But wait a minute. When I do sine of AT, it's A over s squared plus a squared. If we have s squared plus 49, what's A? Oh, crap. I got a 5 on top, not a 7. 2. Like just unfortunately, it's s squared plus 49. And even if I did try and square that, then I'd get square root that. I wouldn't be able to distribute square root like that, right? The square root of a sum is not the sum of the square roots. The cosine has an S on the top. We have a 5 on the top. Oh, I like the fact the top is a number means I'm probably better off using number 4. But I need to fix the number, right? So I say to myself, it would be ideal if that was a 7 on top. So what I'm going to do is I'm going to take the 5 out front. And now, just like I did with the 2 over 2, I'm going to put in the 7 I need, right? If I put the 7 there, what goes out front? 1 over 7. So the answer is 5/7 sine 7t. Noah, if I had something like this, this is a combo, isn't it? How am I going to take care of this? I'm going to split it up into 2 separate fractions. The 2s over s squared plus 9 and the minus 6. So they're just going to be split apart, just like we did with the t and the 2t to the 4th up here. I'm going to use my linear property. Now, if I want to use the sine of AT, if I want to use the sine, what should be on top in this fraction? 3, but I have a 6. So let's take out a factor of 2. Here, if I want to use the cosine, the only thing that should be on top is the s. I will also take out a factor of 2. Well, now, this gives me 2 cosine 3t minus 2 sine 3t. So I can think of this term by term separation and rearrangement in whatever fashion I want, as long as I can break it into pieces that look like these. Questions? Let me put back up this list so far, because this list is big, but we've only done the stuff in 7-1, right? So I've only done the first dozen of these, or at least been exposed to them. We didn't actually compute all of them, although you did some of these for homework. S minus A, S to a power, squares, things that are linear but to a higher power. Hey, wait a second. Look at all of these things we've got over here. Where have I seen these functions of t that I see in that left-hand, well, center column? Those are things like my non-homogeneous terms, aren't they? Didn't we have e to the t and a cosine and then a quadratic thing in the exam? So we've seen crap that looks like this in our differential equations. So if I do the Laplace transform in a differential equation, I'm going to be doing the Laplace transform of those sorts of things. And then when I undo the Laplace transform, I'm getting things that look like my solutions, aren't I? Hey, wait a second here. The whole point is that if I can do a Laplace transform and then do the algebra to figure out what the solution is, I don't actually have to do the integrals in the differential equations anymore. All of that variation of parameter stuff, all of that unknown, undetermined coefficient stuff, bye-bye. What's it replaced with? Algebra. Problem. It is quite possible that when I do one of these things, I could end up with a fairly ugly Laplace transform. And I picked this one on purpose. 0.9s over s minus 0.1 s plus 0.2. Because when I look back at this formula sheet, I see s minus a on the bottom. And I can think of s plus 0.2 as s minus negative 0.2. So that's still an s minus a. Talk to me, Mia. Yes, my handwriting sucks. I apologize. What I don't see anywhere on here is a product in the bottom. Please notice in all of these Laplace transforms, all the way up through number 12, I've got s minus a, s squared plus a squared, s squared minus a squared. I've got s minus a to a power. I don't have s minus a and s minus b in the bottom. And that's really what this is. So how do I make that look like this? I got to go back 2 whole semesters, maybe more. The right thing to do to simplify this is to do partial fractions. Yay! Like I said, we're replacing the integrals with Calc 2. You are. Wait, Noah, I'm a little bit nicer than that. So not only did I put the formula sheet on our Canvas page, but I actually put the entire review of partial fractions from the calculus book on our Canvas page. Because we're going to need it. All right, wait a minute. 0.9s over s minus 0.1, s plus 0.2 is going to be a over s minus 0.1 and b over s plus 0.2. I remember how to do. I remember doing this. I don't necessarily remember how to do it, but I know I did it in Calc 2. What do I do from here? cross multiply. Multiplied by my lowest common denominator, and I get A S plus 0.2 and B S minus 0.1. And over here on the other side, I just get the 0.9 S. Gotten rid of the denominators. Well, now I can rearrange, and I have 0.9 S is A plus B S, and then plus 0.2A minus 0.1B. And now I have two equations in two unknowns. The coefficient of S has to match the coefficient of S. And the constant has to match the constant. What's the constant on the left? Bing. So A plus B equals 0.9, 0.2A minus 0.1B equals 0. You know what? I'm going to multiply that bottom equation by 10. 2A minus B equals 0, because 0 times 10 is still 0. And then when I add, I get 3A equals 9. So I get A is 3. And then I know what's B. Oh, wait a second. I didn't multiply the top one. That's 0.9, 0.9, 0.3. What's B? 0.6. Which means this fraction, I'm now asking for the Laplace inverse of 0.3 over S minus 0.1 and the Laplace inverse of 0.6 over S plus 0.2. But that's S minus A both times. S minus 0.1, and this is S minus negative 0.2. And that means those are E's. But when I do the E thing, it's usually a 1 on the top, right? So I pull out the 0.3. And I pull out the 0.6. And I get 0.3 e to the 0.1t plus 0.6 e to the negative 0.2t. Look at that. A transient solution and a non-transient solution, and we solve for C1 and C2 right away. Problem is, I got to do a whole crap ton of partial fractions to do this. There will be a lot of algebra in the next couple of weeks. It turns out that if I want to use these to solve a differential equation, I need to be able to do one more thing we haven't done yet. I need to be able to figure out how to take the Laplace transform of a derivative. Please notice the grammatically underlined phrase. I can't do this without initial conditions. To use the Laplace transform, I must have initial conditions. It turns out that with a bunch of integration by parts, I can actually do the Laplace transform of f and of f prime, and they're related to each other. Now, something interesting, a continuous function could have a derivative that is discontinuous, right? Like the absolute value of x. The absolute value of x has a discontinuity in its derivative at 0 because of the corner. But that's still piecewise continuous. It's continuous everywhere to the right of 0 and everywhere to the left of 0, just not at 0 itself. Gesundheit. And it turns out I can still do a Laplace transform on f prime. The result is going to include part of the Laplace transform of f. Now, I have skipped about 8 lines of calculus here that's in the textbook, but I didn't want to just write and just spew a bunch of integrals over here on the board and have you stare at me going, what the fuck? Because really, I don't need you to know how to do this. I'm just going to tell you, we did this integral. It's on page, I didn't write down the page number. That was dumb of me. It's on page 296. But notice, we end up with an extra s here. If I do it again for a second derivative, well then, I don't end up with f of 0. I end up with f prime of 0. I also end up with f of 0, but there's an s next to it. And then there's an s squared next to the Laplace transform of f of t. Why would it become s squared? Because I iterated the whole procedure and I got an extra s from going from f prime to f double prime. As a matter of fact, this is true no matter how many derivatives I take. On our formula sheet, this is formula number 13. If I'm taking an nth derivative, I get s to the n times the Laplace transform. And then 1 less power, f of 0. 2 less power is f prime of 0. All the way down to no s's, one less derivative. Those are all my initial conditions on the right-hand side. That's why I have to have initial conditions to do this. All right. So how the hell does this work when it comes to actually solving a differential equation? Ready? I'm going to give you one you know how to solve. That's a little too light to really read. Let's switch colors. Okay. This is a first order differential equation. I don't have to do it with Laplace transforms. I could use an integrating factor, right? I know what to do. But I'm going to do the Laplace transform. So on the left side, I'm going to do the Laplace transform. And here, I'm going to get L of y prime minus L of y. And on this side, I'm going to get L of 1. What's the Laplace transform of 1? 1 over S, period. It's just 1 over S. But according to this, the L of y prime is minus y of 0 plus S L of y. Hey, notice that on the left-hand side, there's nothing about a derivative anymore, is there? The only Laplace transform you have on the left is the Laplace transform of y, the Laplace transform of the solution I'm trying to find. What's y of 0? Ah, great. So this is 0, which means the left-hand side is S minus 1 times the Laplace transform of y, and the right side is 1 over S. I now know the Laplace transform of my solution. The Laplace transform of my solution is 1 over S times S minus 1. And now I can ask you, what's the inverse of that? The inverse Laplace transform. So I know that y is the Laplace inverse of 1 over S, S minus 1. If I can find this, I'm done. No integrating factor, no solving for C or K or any of that garbage, just the algebra, undo the Laplace transform. But in order to undo this, what do I need to do to this thing inside parentheses here? Which means partial fractions again. Cross multiply by the common denominators, multiply by S and S minus 1. I get a 1 on the left. I get A times S minus 1 because the S cancels. I get B times S because the S minus 1 cancels. And that gives me A plus B times S minus A is equal to 1. What's A? Say again? It is. What's B? Because there's no S's on this side, so A plus B has to be 0. And if A was negative 1, A plus B is 0, B has to be 1. Which means the Laplace inverse I am looking for is negative 1 over S plus 1 over S minus 1. Wait a minute, 1 over S came from 1, but there's a minus sign there, right? So I take the minus sign out. And this gives me minus 1 plus, I can't quite hear you tonight. The sign has the squares in it. That doesn't, so that's just an E. It's e to the 1t. if I did this the way we learned back in chapter 2, I would have found the integrating factor. The integrating factor would have been e to the negative t. And then I would have multiplied everywhere by e to the minus t. And then I would have integrated and I would have gotten minus e to the minus t plus c. Then I would have had to solve for c, which would have given me c equals 1. Then I would divide by e to the minus t. That would give me minus 1, e to the minus t divided by e to the minus t. Those cancel. And 1 divided by e to the minus t, which is 1 e to the t. I never had to integrate. I never had to solve for the constant. It was all done automagically by Laplace. All I have to do is the partial fractions algebra. As long as I can do this algebra here, this saves my ass a whole lot of work. Questions? Now, this is a second order differential equation. Again, I already know how to solve this. This was one of the first ones on the first page of the exam, right? I know how to do this. But let's try it the new way with the Laplace transform. I'm going to take the Laplace transform of all of the pieces here. L of y double prime plus 5L of y prime plus 4L of y equals L of 0. But the Laplace transform of 0 is 0. So I'm doing an integral, multiplying everything by 0. That's easy. So the right-hand side is going to be a 0. But let's look at the left-hand side. What do I get for my f double prime? Y double prime in this case. Oh, that's here. Formula 13. So I get minus y prime of 0 minus sy of 0. I'm sorry. Yes, that's minus. And then s squared, right? The s squared is what's plus. Now, as soon as I say that, I think I made a typo back in the previous one. Let's go back and look at the formula sheet here again. And I see, yes, this one is positive and all the rest of these are negative. That means back here, this should be a minus sign. Plus 5 times Laplace transform of y will be minus y of 0 plus s Laplace transform of y plus 4 times the Laplace transform of y equals 0. Okay. This is a number. What's this number? Sure. That's the derivative, so that's 0. This is a number. That's the 1. So I have minus s times 1, then s squared L of y. Then here I have 5 times, well, that's a 1, right? Minus 1 right there. So that's minus 5 plus 5s L of y plus 4 L of y equals 0. I apologize in advance for having s's and 5's in the same problem. If this pisses you off, change the letter. Just don't use t, because we're using t for the other part of the transform. I'm going to put everything that has an L of y on the left and everything that doesn't on the right. So on the right, I'm going to get s plus 5. What's on the left? Which means I have L of y. L of y is s plus 5 over s squared plus 5s plus 4. Please notice that the denominator here is our auxiliary equation, isn't it? R squared plus 5r plus 4 would have been what we got from the original equation. But that factor's on the bottom. S plus 5 over s plus 1, s plus 4. Again, if I do partial fractions, I can do the inverse transform. Now I'm going to cheat. And I'm going to tell you that when I do the partial fractions, I get 4/3 over s plus 1 minus 1/3 over s plus 4. You should leave yourself room and make sure I'm not blowing smoke in your ear or other orifices. But now I can do the inverse transform because this is L of y. So y is 4/3. Okay, that's s plus 1. What's the inverse transform from 1 over s plus 1? This is why you need the formula sheet in front of you. Because it would be s minus -1. So yes, that's e to the minus t. What about for the s plus 4? I never had to find a C1, a C2. I never had to solve for them. I didn't need to do any of it. I did the partial fractions instead. Now, I'm the first person to admit the way we would have done this on the exam would have been easier, right? That's for a second order. And it was homogeneous. If it's not homogeneous, then it's a lot uglier. I either have to do undetermined coefficients or variation of parameter. No, not anymore. I just have to do the transform and then the partial fractions. And that is going to be much easier. For non-homogeneous equations, it's also going to be much easier for higher degree equations. Remember the bonus question on the exam? Y triple prime, fourth derivative? Fourth derivative, right? Ooh, be much easier this way. Especially if that was non-homogeneous. We'd be there for forever. This gets better because the Laplace transform works on functions that aren't continuous. It works on functions that aren't even very nice at all. And it still allows me to solve directly. It replaces big, ugly integral work by algebra work instead. Please review your partial fractions discussions. I will see you all tomorrow. Have a wonderful rest of your day. I have your exam if you came in late and I